Hello Matrix, welcome to yet another video. We are back to Term 2 materials. Remember, Term 1 is not to be forgotten, so please review all videos that I made for Term 1 for you to get a maximal benefit on work for Term 2. Otherwise, we just keep the steam train moving. So if you want the best mark for your Term 2, please pay attention. So I picked this paper from Mpumalanga for Term 2. Of course, it is more of your paper 1 in general, 150 marks over 3 hours. So it's going to be a walk. All right. So I'm only doing papers, guys, because of availability to me, not necessarily specifically pushing a particular province. So Mpumalangas, as you have really blessed my channel with, your best of corporations. Now I'm giving it back again, thankfully. So we have got ourselves a situation here where we do not overlook instructions. So most of them are pretty straightforward, but please read them all. Most important are the ones I have highlighted. So you are advised to use your data sheets, meaning if you feel like you can't go on, please check there. You might find something that helps. And then, of course, show all formulae and substitutions in all calculations. And then round off your final numerical answers to a minimum. Minimum means 2 or more decimals, no less than 2. Then give brief motivations, discussions, etc. where required. Okay, so let's get to the paper. So, of course, having read the general instructions, it is important, but it's also important to read local instructions. So here we're told various options are provided as possible answers to the following questions. Choose the answer and write only the letter A to D next to the question numbers 1.1 to 1.10 in the answer book. And we're given an example of how this works, okay? So each question has only one correct answer. Please let that sink into your brain. Now let's see. A ball is thrown vertically upwards. Okay? First of all, it is thrown. It's not dropped. Okay, so it is thrown. So if it is thrown, it becomes a projectile. Okay? Because it gets some initial velocity. So now let's think this is the level of the ground and this is the ball being thrown upward, okay, with the velocity v. And then of course it will go, reach maximum height, and then it will come back down. But somewhere in its path, okay, let's just go down for a second. No, that's not a rugby ball, man. It's a soccer ball. Okay, so that is the sketch we have in mind. So if we choose upward as positive, remember, we were told nothing else except that this ball is thrown upward. So there's a lot of things going on. First of all, if we draw a free body diagram of this ball, in this section, from the moment it is launched until the moment it reaches maximum height. Of course, at maximum height, there's a bit of a change of things. Okay, so it's the weight of this ball acting straight down. And then we've got air friction or air resistance. And it always opposes the motion of the ball. So we can just say friction here. Okay, or let's just say FA to suggest that this is air friction. Okay, so both of them are directed down, meaning they're going to give us an acceleration that is directed down. Why? Because the resultant force is downward. Okay, great. And we know that the acceleration is not G because there's an extra force in there. All right, and when we reach maximum height, this is when the ball stops. Okay, and as it stops momentarily and then it changes direction, and immediately it does that, what is the story? The story is that on this side, it's when the ball is moving down. So there's a switch. The gravitational force is directed down as always, but now F friction opposes it because now it's opposing the direction of motion of the ball. Okay, don't worry about stuff being, stuff in here. So again, we will still have acceleration directed down. Great. Okay, that's cute. So what is happening here? So when this ball momentarily stops here, okay, what happens? It's no longer moving upward and it just stops momentarily. And we know very well that if we draw a free body diagram at that point of the maximum height, we know that it will only be experiencing just gravitational force. Okay, so meaning the acceleration here is g. That is directed down. So guys, I know I take forever to do things. So this is what is happening at the maximum height. Because when it stops, it's no longer moving. So air friction does not affect anything until it starts moving down. But we also know that there's a lot of swings and, we know that at some point before this ball reaches the ground, let's just pick this portion here. And say from this point on, we know that the air friction will have caught up with gravitational force. So there is a point during that motion where we know that the gravitational force is going to be equal to air friction. Okay? And then it does something called terminal velocity. Okay? It does some terminal velocity. I don't know, my writing just likes to fade, or I don't give it enough chance to come out. Terminal velocity. Okay, so this is a constant velocity of a falling body when air friction or air resistance catches up with the magnitude of the gravitational force. And since the resultant force here is zero, it does terminal velocity, and that simply means zero acceleration. If it's zero acceleration, it means there's a zero resultant force. Okay, so this is some of the things that happen, and we know for a fact, if we think about the time frame from, say, 0 to reaching maximum height, let's call this one T1. And then let's consider the time frame of coming from the maximum height to the ground. Let's call that one T2. So what can we say about those two? Of course, guys, I'm taking a bit of time. We know for a fact that since the magnitude of acceleration in this instance when it is falling down is going to be less than the magnitude of acceleration when it was going up because of the resultant forces involved. And certainly reaching a point where it does constant velocity, and it tells us that definitely T1 will be less than T2. Okay, so there is no time symmetry in this instance. What else can we learn? We will also learn that the velocity with which it left the ground and the velocity with which it reaches the ground are not equal. So we can call that one the initial velocity, and then we call this one the final velocity. So we know that the initial velocity is greater than the final velocity. Okay, please remember that when no conditions were given, this is so much intense. There's a lot going on. But let's answer the question, which was our mission here. I just took the liberty to educate you a bit. Now the question says, which one of the following physical quantities is not equal to 0. So which one is non-zero in here? We can obviously tell that the acceleration is downward. It's still accelerating at the maximum height due to gravity. It accelerates again due to some, combination of gravitational acceleration and, influences of air friction, until it does not accelerate at that point when it does the terminal velocity. So essentially, the question now is related to the maximum height. So greatly, at the maximum height, we know that we have gravitational force as the resultant force. We also have g as the resultant acceleration. So now the question says net force. True, because we still have gravitational force at that point. Even though air friction falls off momentarily there, the momentum cannot be 0. Why? Because momentum is the product of mass and velocity. We know that at the maximum height, the velocity is 0. Okay? So now that product becomes 0. And then the velocity is definitely 0. Kinetic energy, we know that EK is equal to half mv squared. Since the velocity is 0 at the maximum height, that whole product becomes 0. So our answer here is A. Okay? So of course, you could have answered this question quickly if you understand, but I'm just trying to help you review a few concepts. So don't kill me for it. Now we're told here an object of mass m stays at rest. So once we say something is at rest, what are we suggesting? We are suggesting that its velocity is 0. Okay? Now on a horizontal surface, when a horizontal force of magnitude F is exerted on it, as shown in the diagram below. Great. Now we can see that the force is going to the left. Obviously, if it is at rest, there's a force balancing it. And what would be that force? It's static friction, isn't it? Yes. So we are told here the force increases, but the object still remains at rest. Okay, so why? Obviously, it says we have not reached the maximum frictional force that is due to this object's weight, or should we say the normal force generated as a result, and of course the coefficient of friction of that surface. So what is the story then? We're told here, which one of the following forces also increases as F increases? Okay, is it the normal force? Remember, the normal force and the gravitational force are vertical, or should we say they act perpendicularly. Okay, let me try to make it vertical. So remember, the gravitational force, don't worry about the little thing is there. It's not doing the things. So we know that Fg and the normal force are perpendicular to the surface, and essentially they don't get affected by a horizontally acting force, F. So it can't be normal force, it cannot be gravitational force. What about static frictional force? Okay, so technically the static frictional force, remember, will essentially increase, because it means when we started with that lower magnitude, we were at some minimum static frictional force, because by increasing it and still not moving that object, it means it increases by approaching its maximum. Okay, it increases to approach its maximum, and if we reach maximum and we go beyond that, then the object will start moving. Kinetic frictional force, remember this one is 0. Why? Because kinetic friction is friction of a moving object. Okay, so the answer here is C. So always remember all of these things so that you can answer in the best way. 1.3 says 3 objects X, Y, and Z are accelerated okay, in a straight line on a horizontal surface. The following momentum versus velocity graphs represents the movement of each object. So we can see this graph is for x, and now we see that the momentum is on the y-axis while the velocity is on the x-axis. So what is happening? Well, the formula that governs all of this is this one. Momentum is the product of mass of an object and its velocity. Now, the question says, look, if this is on the y-axis, right? And then we've got the velocity here, which is on the x-axis. So obviously, what would be the gradient? The gradient is the mass of the object, because that's what stays constant here when we vary the momentum as well as the velocity, because those are the two variables. So m becomes the gradient. And as you can see here, the gradient is quite constant because it's not changing. Great. So how do we make sure this is the case? We simply work out m here. We divide p by v. So that's how we find that expression that actually says change in y over change in x will give us the gradient. So that's what works the magics for us. All right, now that we understand what we're dealing with, so let's have a look. It tells us now, look, the gradient of x. Can you see it's higher than the gradient of y? Because it is very steeper than the gradient of y. Why? We also see that z's gradient is less than the 2 as well. So that tells us the masses are not equal, meaning the mass of x is greater than the mass of y, which is also greater than the mass of z. That's what we can learn from the graph. Okay, let's move on. Which one of the following statements is correct? The masses of the three objects are equal? No. We can already tell the gradients are not the same, and those gradients represent the mass of each object. Now, object x has the smallest mass. No, it has the greatest, because we can see the gradient is the steepest of the three. Okay, object y has the smallest mass, not smallest, but intermediate in this system of three objects, so it is not the smallest. Object z has the smallest, definitely, because you can see the gradient of z is gentler than the other two, so it means its mass should be smaller. So whenever you're given a graph, try to understand it in terms of what could be the equation that governs, some of the dynamics there. Let's look at question 4. A ball of mass m is dropped from a height h, okay? So we've got a mass m from some height h, okay, above the ground. It is dropped. So when we drop it, we know that initial velocity is 0. Okay, after it moved distance x, its the kinetic energy of the ball is, okay. Now these are some of the higher order questions where you can't just, sniff an answer and get it right. You've got to do some working out somehow. Okay, let's have a look. We've got ourselves a situation, okay, governed by this scenario right here. So we've got this height. So that is the height h. And we've got our ball being dropped from that edge, where the initial velocity is 0. Because when you drop something, it is essentially at 0. And then of course we know that when we reach this point here, we can tell that this distance that it traveled is called x, okay, meters. and it's a vertical distance. Okay, so we want to know the velocity here, basically. Not this one, but we want to know the velocity there, because that velocity will help us to work out the kinetic energy, because we know what kinetic energy is. But if we think about it, there are two scenarios that can fit this given scenario here. We may have a similar situation here, where of course our object moves this distance x on this side, but we have a free body diagram that is different for each of the two objects in both the scenarios. So here we could have ourselves a situation where gravitational force is being opposed by air friction, whereas on this side we could essentially just have only one object acting, only one force acting, where we ignore the effects of air resistance, so we're getting the gravitational force only. So now, because they didn't talk about ignoring anything, so you always consider all possibilities. You don't want to mess up. So basically we also want the final velocity there, as that final velocity will be very useful in helping us to work out kinetic energy. So which ones of the two scenarios, guys, do we choose? Because we know here the resultant force, it says that we have g as the acceleration, which is directed down, okay? But here, acceleration is a. Yes, it's down, but it's definitely not g, okay? So what do we do with a scenario like this? This is when you try to look for clues in the given information. What do we notice about these options? They've got g. Okay, they've got g, and we've got our mass m. All right, so meaning this mass is included in this calculation somehow. All right. Now, that can almost tell us that the acceleration we probably are dealing with here is this one, because we can see here there's h and x, there's x alone, and then there's just h alone. So most likely we are looking at this scenario. Okay, so sometimes you try to look at what you are provided to kind of milk out what are the possibilities. Now let's try using this one. Of course, it's always trial and error when it's like this, so you may have to test both possibilities. But in this instance, we know that the final velocity squared is equal to initial velocity squared plus 2g delta y, isn't it? We're using equations of motion. So this is 0 squared plus 2 into g. But now the delta y here is x, okay? Obviously, we're choosing down as positive. Remember that. Sometimes with this directed, thing is, you want to make sure you work out things. Therefore, we know that the final velocity is going to be just the square root of 2gx. Do we agree? Now, if one kinetic energy is going to be half m, which is the mass m, the velocity squared is the square root of 2gx, and then squared. Then what happens here? We've got half of m into, when you square this, you just get 2gx. And then the 2's cancel, and all we have left here is basically mgx. Now, that is the answer we are getting here. Do we see something like it? There it is. And if you spot it, there's no need to look for another scenario, because we'll be wasting your time. But of note here, what will help you to understand what's going on here is to work out what the acceleration would be. And the acceleration is going to head, because we know here from Newton's laws of motion, it's going to be a, okay, let's write it in that scenario. I just want to show you something so that you can understand why it is not fitting. Here, if we want acceleration it's going to be the difference of these two forces. Of course, G being dominant is going to be Fg minus Fa, okay? All of that divided by M. Okay, if we try to work it out, Fg is basically Mg, and then we're dividing by M minus Fa divided by M. That's how it works, and that works out. It's going to be G minus some ratio of Fa over M. Now, do you realize we don't know what this is, the value of that? So it's very difficult to use this, because at some point we may need to use that acceleration. And because of this guy right here, we are unable to go further. But what is of note, which I would rather you make sure you understand, is the fact that whenever you're accelerating downwards and there's two forces involved, say gravitational force and another force, the acceleration is less than G, okay, because you're going to take something away from G. But when you're going upward, okay, the acceleration is always going to be G plus whatever you would be getting there, all right? So meaning it is greater than G. So please remember those things. Sometimes they can help you when you get some of these silly questions along the way. Okay, let's move, guys. Now we are told here, a rocket of mass m is launched from the surface of the Earth and radius r, okay, of radius r at a distance 2r. Above the surface of the Earth, the mass of the rocket is half m. Okay, that's pretty strange, don't you think? How can the mass of a rocket change? Remember, the rocket has fuel that it consumes as it goes up or as it goes further. So technically, as the fuel level drops, the mass of that rocket will drop. So it makes sense, because if you watch racing cars as well, they'll be telling you at the beginning of the race, the car or the race cars are a bit heavier, so they tend to be a little bit more difficult to accelerate around, because then they consume a lot of fuel. But as you get to somewhere, a half race distance, the gas mass there has dropped, and therefore it's much easier to accelerate, and it chows less of the tires in a way. So it's one of those things. Anyway, so that makes sense at least. So it's not really some crazy situation. Now we can see there that, look, the radius is from center, right, to circumference. So any distance from center to circumference is the radius. So it doesn't matter that they chose that one. They're just trying to mess with you. So we know that we've got r here, and then to where this rocket is, which is now the distance of 2r. Okay, so basically this rocket, how far is it from the center of the Earth? It's 3r, because we're going to add those distances together. Okay, so now I told you the magnitude of the gravitational acceleration of the rocket now changes to, remember, gravitational acceleration is given by small letter g equals capital letter G, the mass of the Earth, over the radius squared, right? Right. So this gives us m. But now what would be g in the next instance? It's going to be g m, right, over. But now the distance, remember, the gravitational acceleration is independent of the mass of the object. But I will show you why. And then here we've got 3r. Okay, and then we square that. What happens? We get g m over 9r squared. So when you factor out this ratio of 1 over 9, we end up with gm over r squared. This, we know for a fact, is the same as that, right? So that represents g. So this is 1 over 9 g, okay, or times g. And then if you're multiplying by g, this is g over 1. This means g can be on the numerator. So which one looks like that? Is essentially this one, but they made a mistake here. The half doesn't play. It's not a part of this, but this is the best answer because these are calculation-based type of, considerations. If you don't perform a particular calculation, it can throw you off. So why am I sure that the mass is not involved? Remember, if you want the gravitational force, it's going to be mg, okay, equals the big G times m of the earth times m of the object divided by the radius squared, or the distance between the two. So if you divide by m, this one goes and that one goes. So all you end up with, G is just G m earth divided by radius squared of the earth. So this is why no matter you put a half m here, you will still put a half m, it cancels out. So there was a bit of a situation there. Anyway, let's move on. Astronomers observe the spectral lines of a star, okay? Now we're doing Doppler effect in terms of the stars or the universe. Which one of the following describes the effect of the Doppler shift on the spectral lines if the star moves away from the Earth? So when you're moving away from Earth, we know we talk of the so-called red shift. Okay? So now it says the spectral lines appear to be dimmer. It's not about brightness of the light itself. They undergo no change. That's not true. There is always going to be a change if we're talking about some Doppler shift. Are shifted to the red end of the spectrum. That's definitely true. They are shifted to the blue end. Remember, a shift to the blue end means towards Earth. Okay, so basically the answer here is this. So this is a straightforward question. No time wasted. No time wasting there is necessary. So 1.7 says a positive point charge placed halfway between two charges X and Y. Okay, it's a positive point charge. We are placing it between two positive charges. No, they didn't tell us what is the characteristic of these charges, but we know that it's between X and Y. Okay. Now it says, which one of the following will the net force, meaning the resultant force of on the point charge, this particular one, be the largest? So we want the greatest. Now let's think about it. This is all related to Coulomb's law. Right. So what do we know? What would be the relationship of this charge and this, positive point charge? They will repel each other. So this positive point charge will experience a force in that direction due to charge X. But it also experiences repulsion from that point charge, Y. So as a result, if we're looking at these two, these two are equal. I don't know why this thing likes to jump. Don't do things when these two are equal, because this is 1 nanocoulomb, and whatever magnitude this positive charge is, again 1 nanocoulomb plus whatever. And remember, the distances are the same, so those forces are going to be the same but oppositely directed, such that the resultant force is 0. Okay, so that is basically the smallest, I guess, at the moment. Then let's look at this one. So we've got 1 nanocoulomb and whatever charge this is. But again, this is a positive charge on a positive charge. It's going to experience a force in that direction, right? But we can tell now that the magnitudes are not the same. So maybe we can call this one X. Okay, because it's from 1 nanocoulomb to whatever that charge is, but the distance is the same between the two. But what is different now is the fact that this is a positive charge, so it's going to push that positive point charge in that direction. But we know that the resultant force or the electrostatic force is actually directly proportional to the magnitude of the charges. So if we double the magnitude, this becomes 2x. Okay? So as a result, the difference here is just going to be x. Of course, in that direction. Well, this is a vector because 2 minus 1 is just x. Okay? Now let's check this one. Now this is a positive charge, this is a negative charge, so it gets pulled in this direction. Okay? But because there's a 2 in there, so it's going to be 2x. But again, this charge will experience a repulsive force from x. And we can call this one x, And we can see that the resultant force here is going to be 3x and to the right. So this is most likely the biggest, because look at this. This one will experience being, okay, we can call it x here because it's 1 nanocoulomb on 1 nanocoulomb. Forget the sign at this point. But it's an attractive force, so it's going to be towards y, while it's going to get a repulsive force of x from that x point charge. Now the resultant here is going to be 2x to the right. So which one is the greatest? Is C. Okay? So please guys, know the proportionalities and how they can affect magnitudes of certain calculations. Let's just move on without wasting time. Point Z is a distance D from Point Z is a distance D from a charge Q. So okay, we only have this charge here. This is the charge. The rest are just positions around that charge. So these are points on the electric field, basically. Now, we're told your point Y is halfway. So, point Y is halfway between Z and the charge Q as shown, okay? So that's fine. Then we're told here, the electric field at point Z is E, okay? Not a problem. We take it. Now the electric field at point Y is. So what the electric field at point Y? So what do we know? We know something like, what do we know about point Z? We were told that the electric field is E, but how do we do the electric field? Electric field is basically K, the charge involved, over the distance between the charge and that particular point at which you're measuring the electric field. And we were told that this is E. So meaning this is basically, no, this is not correct. I'm making a mistake here. So this is basically, at first it's going to be K, Q, divide by, now what is that distance? Is D squared. Okay, because they said the distance is D. Now, what we formulate is the fact that this ratio here represents the answer that we were given, that it is E. Okay, so we're getting that expression for E. Now, what do we want? We want the resultant force at Y, because the electric field, it's a vector. Now, what do we understand? Y is basically half D. Okay, so from Q to Y, it's half the distance. So let's see what is the story in there. So we know that if we want the electric field at Y, it's going to be K, of course it's the same charge, over, now the distance is half of D, and then we're squaring that. What do we get? It's KQ over, this one is 1 over 4, sorry. d squared. Okay, great. So when you divide by a fraction, it literally flips to multiply in front. It becomes 4k q over d squared. Okay, so basically what is that? We know that this represents E, so this is the same as 4E, and that is D. So you can't answer this question if you did not perform a little bit of some calculation. Okay, let's move on to 1.9. Now we're told here a cell with an EMF E is connected as shown in the circuit diagram below. The switch S is initially closed. Okay, what do we understand? We know that this is the positive terminal of our battery, whereas we've got our negative terminal of our battery. Okay, conventional current goes in this direction, and then when it gets here, it splits because this is a parallel connection. So depending on the magnitudes, it will split such that the least resistance gets the most current split. Okay, at the end of the day, it comes here and they come together to complete the circuit through the battery again. All right, so that is the story. So we're not told anything about internal resistance, but in any case, we know that there is always an internal resistance because we are moving current or charge against some sort of a gradient. Now let's look at this one. The switch S is now opened. So when we open this switch, what happens? That means we're cancelling this section. The current doesn't pass through there. Creates a high resistance, won't even reflux back. So it means current will only move on the complete circuit only. So it moves that way. So we're cancelling out this resistance. Now the question says, which one of the following represents the changes in the EMF and the total resistance? So the reality is EMF is a constant. So it never changes. So it cannot change. So anything that says remains the same is good. Anything otherwise is already out. So we are wrestling with those two options, A and B. But then what happens to the total resistance? We know for a fact that when we have a parallel connection, the effective resistance is smaller than the smallest of these, combinations. So the resistance is usually smaller with the parallel connection. But as soon as you take out the parallel connection and you leave the resistors involved in series, what happens to the total resistance? It increases. Okay, now what is the relationship of resistance? We know that V equals IR. So if we keep V constant, because at this point we were not told anything about internal resistance, this V is effectively the EMF E. Okay, so that being constant, it means these two are inversely proportional. All right, so as we increase the resistance, what happens to the current? The current drops. Great. So the total resistance increases, we said. Oh, great. So this one is all about resistance and nothing about the current. So the resistance doesn't remain the same. It doesn't decrease. It increases. But the option that ticks all the boxes is B. All right, guys, let's do the last one. I know I took a bit longer than 30 minutes. I'm essentially 14 minutes late. It's fine. Observe the following circuit. Okay, again, please analyze. Don't be lazy. I know you like shortcuts, you guys, but shortcuts will leave you hanging. This is where you are creating a genius in yourself. So you just want to not cut the corners at all. So conventional current is from the positive terminal of our battery all through the circuit back to the negative terminal. But now we know that voltmeters in general, now remember here you need to be able to know certain things unless stated otherwise. Observe the following the circuit diagram. So we know that voltmeters are extremely high resistance devices, so that current does not pass through. So even if this switch is closed, no current passes through here. The current will just bend here and move through the 4 ohm resistor, and then when it gets here, because now there's a parallel connection, the current may split into those two, and depending on the magnitudes involved here on this parallel connection, the least resistance will get the most current split, and then the currents will come back together here, all right, and go in that direction. Okay, of course, considering that this is opened. Okay, but when it is closed, the current always looks for the least resistance. It will actually short circuit the 4 ohm resistor if you close that switch. And if you open this switch, the current doesn't even come through here. But we're just looking at possibilities right now. Okay, great. And then after all has been done, it comes back here. But now if this wire here, if this wire is connected and that switch is closed, that means we'll bypass all these resistors underneath it. So the current will only pass through the 4 ohm resistor and back to the circuit, back to the battery. So the question says now, which one of the following switches must be closed to increase the power in resistor R the most? Okay, so what is our reference resistance here? Is resistor R. Okay, we want to increase the power in there. So how do we increase power? Remember, power is I squared R. So resistance is essentially constant unless somebody tells us something else. So that means the variable here is basically going to be power and current. So for us to increase this situation right here, we need to increase the current basically. Now, how do we increase the current? That means we must drop the effective resistance of this circuit. And to drop the effective resistance of this circuit, we either create some parallel connection or we eliminate a particular resistance, because it will depend on the dynamics. So meaning we cannot go this route. So switch S is a no-no. Okay? Because if we close switch S, that means we're eliminating this resistor of interest. So we'll never know what happens. In fact, nothing happens, all right? So switch S is a no-no. Sorry, S4. So it's already out. Now, do we close S2? Because we said S1 doesn't make any impression. Whether you open it or you close it, the only thing that would happen is that if you open it, we read 0 voltage here. But when you close it, it will have a value, but no current will pass. So switch S does not affect anything. S1. Now the question is between S2 and S3. Which one do we close? So if we close this one, we will have a parallel connection here, right? Right. So this parallel connection is in series with those two. So basically, when we close S2, what would be the resultant resistance in the circuit? We know that R tot is going to be this one and that one because they're in series. So it's going to be 8 plus. Now these ones in parallel is always product over sum. So it's going to be 4R over 4 plus R. All right. Whose value we don't know. Okay. We don't know what this value is. Okay. But we know those two will add up together if we're saying we're closing this switch. So we want to know what would be the value of this thing. What would be the value of this thing here? Now that gives us a bit of a situation. And then if we close S3, what do we end up with? We bypass this. So that means we eliminate this 4 ohm resistor, because current will always choose the least resistance. We know connecting wires, normally they have the least resistance. In fact, it's negligible. Now let's move on. What happens here? The total resistance becomes this 4 ohm resistor plus basically the value of R alone, because we chose to close S3. So meaning there's no current passing through the 4 ohm resistor. So we have these ones in series. So it's only those two. So again, we're saying what should be the value of R? Then we can just assign a value for R that works for us. But we have a bit of a situation. We are unable to tell that R must be bigger than these 4 ohm resistors, or should be the same, or should be less. It doesn't matter. Now let's vary the values of R to check what happens in each scenario. If we say R, for example, is 5, then 4, then 3, because we want a value that is greater than these other resistors. To check what happens if we increase that value, we check what happens when we have an equal value to these resistors, what happens when it is less, so that we can be sure which one works the most, of the magics that we want. So let's just say 8 plus, now we're going to have that situation here. We've got 4 times 5, which is 20, by the way, divide by 4 plus 5, which is 9. Okay, so I'm getting here a 10. So when we're using 5, the total resistance here is 10,22. Okay, but what would be the total resistance here? The total resistance is basically going to be 9. So do you see, when when R has a bigger value, what we end up with, if we include this parallel connection, that means the total resistance becomes 10 over 9. So meaning, if we eliminate S2, we still get a smaller value of the total external resistance. And we are trying to draw something from V equals IR here, Ohm's law. So that if we drop the total resistance, we increase the current, and that's what we want. So in a way, let's see what happens when we put a 4 instead of that 5. So meaning they are equal. So here I get a 10. So when we're using a 4, okay guys, I'm taking a bit of time here to indulge. When we use a 4, what happens to this one? So when we use a 4, we know what happens is that we get a 10 here. Okay? And then what happens here? We get basically 4 plus 4, we get an 8. Okay? So do you see it drops even further? So let's test the last value here to convince ourselves that we're doing the right thing. So what happens when it's a 3? When it is a 3, here, I get a 9,7. Okay? So see, it drops as we drop the values of the resistor R. And then what happens here? So if it is a 3, we get a 7, right? So do you see, sometimes you have to play a game. So these are some of the questions you don't answer, okay? Until you have finished everything, because they will terrorize you. Now we can tell that, look, doesn't matter what value this R is, whether bigger than these resistors or smaller than them, the end result is the same. If we close this switch, we get a higher resistance than when we close S3. So meaning the switch that will actually drop the current, will drop the total resistance, is closing switch S3, then it would be this one. Okay, this one is a no-no because we can see when we close it, either way we get a bigger resistance than when we close S3. So it has to be S3. So as we drop the resistance, we'll effectively increase the total current, and that's what will increase the power in resistor R. So it has to be S3. So the answer is C. So you wouldn't know though the difference between the two. As you could see, you had to play some mathematical tricks. When you have a formula to work with, then you can just choose values so that you can see what are the trends. Then you make a conclusion. So this is more like doing an experiment. So these are questions that truly demand the most from a student. Let me just go drink something and eat something quickly, so that we carry on with question 2. We will take this paper down. Okay guys, so let's carry on. I've had a bit of some refreshments. So we are upon this question. Alright, so we're told here a block of mass 5,3 kgs is connected to a crate. Okay, so we're dealing with a block versus a crate. Okay, we are dealing with a crate of mass M. They are connected by a light and inextensible string T. We already know what that is if you've been following my channel, so I'm not going to go over it. But in short, light meaning it does not add any mass to the dynamics of the system. Inextensible, trying to say that there is no dissipation of any form of energy between the two blocks, such that if they start moving, they move at the same rate. Okay, now a force of 60 newtons, okay, is applied to the block at an angle of 30 degrees to the horizontal as shown in the diagram. The block accelerates to the right, so meaning the direction of motion is this way. Okay, so that is very important. Always make sure you understand, because you would think because the force is being applied in that direction, the acceleration is to the left. Nope, they're trying to tell us that this mass is greater. Then of course we know what is responsible for that is its gravitational force. That is the crate. Okay, so quickly guys, you know that for a fact there's going to be gravitational force of the block and its normal force. And the gravitational force and the normal force are balanced because this object is not going into the table or is not being lifted off the table. Okay, but the other two things to consider is the perpendicular components of this force. All right, so we know that we're going to get our horizontal component, which is Fx, and our vertical component, which is Fy. Okay, and these two are acting perpendicular to each other. So these are some of the things that you quickly think about. Of course, you don't need to be drawing this. I'm just doing it for educational purposes. If you're watching my videos for the first time, by bumping into this one, at least you don't get left behind. But you have a channel now to look into and see if you can learn a thing or two. Now we're told the magnitude of the kinetic frictional force between the block and the surface is 4,83 newtons. And then we're told to ignore the mass of the string as well as any rotational effect. Okay, first question says define the term kinetic frictional force. So what is kinetic frictional force? So we're doing question 2. 2.1, we want kinetic So what is that? This is the force exerted by the surface on a moving object, okay, that opposes the direction of the moving. Come on. Object. Okay, so kinetic frictional force is basically the force exerted by the surface on a moving object which opposes, okay, let's just say which opposes. Of course, you will always find some better words to express this idea, but in short, do consult some exam guidelines. They assist in ensuring that you have some concise definitions, but you're not forced to cram those. As long as you get the science right, it's good. It says now draw a labeled free body diagram for the block. So we can see that this question is forever being asked. So not knowing it is a crime, okay guys, because these are free marks. We got here gravitational force. Remember, certain labels are acceptable as symbols. You don't have to write them in full. Okay, so don't sometimes waste too much time writing things in full. But what is important here, the proportions of these things sometimes is significant, but sometimes it's not. Okay, don't worry, these things are trying to mess with me. So this is basically N, capital letter N is for normal force. And then we know that the tension is going to go in this direction. Okay, and we know that, that force is going to go in that way, which is the applied force. We can just say FA. That is accepted as the applied force. And then we know that there's going to be frictional force. We are moving to the right, so friction always opposes the direction of motion. That is kinetic friction. So FK is an acceptable thing there. So that is the tension. So T means tension, okay? But if you like, you can explain this. It's not necessary though. If you write those, they are accepted to suggest something. All right. So how many marks we're getting there? 5 marks. And you can see there's 5 forces that we showed. So that goes without... okay, whatever, man. Let's not say too much. Now we're told to apply Newton's second law to each of the objects and calculate the mass m of the crate if the tension in the string is 80 newtons. Okay, so that's very nice because they normally let you sweat on your own. So they're giving you a clue here on how to go about it. So let's consider the block. So what happens with the block? Remember, what is responsible for the motion is the horizontal forces. So we don't care about vertical forces because they pretty much take care of each other. So here we've got this block is going to be having, this force here in that direction. What is that force? This is the Fx, isn't it? And it has friction also going in that direction. Of course, these two are difficult to tell apart which one is which. And then we've got the tension. Like I said, vertical forces cancel each other up, so they're not significant. So from Newton's second law, we know that the resultant force equals ma. Okay, this implies, of course, we need to choose a direction now. Let's just say to the right is positive. Somewhere, somehow, you need to indicate that choice. But either way, if you maintain directions in your answers, even if you didn't state, but it helps you to not mess up. So this is going to be the tension minus the sum of Fx plus Fk equals ma. Okay, now let's go for it. Tension, we're given it's 80 newtons, and on this block it's to the right, and then these two, we know that Fx is basically 60 times the cos of 30 degrees, isn't it? Yes, on this diagram here, cos is adjacent over hypotenuse. When you want to solve for the adjacent, it's going to be the hypotenuse multiplied by the ratio. Okay, then we add in here, what is the kinetic friction? We were given there that it is 4,83. This is going to be equal to that block, the mass is 5,3 into the acceleration, which we don't know, so we just leave it as a. And then of course we can simplify things a bit. We're going to have here 80 minus, so 60 cos 30 into, no, plus 4,83. Okay, let's just double check if everything is the way it's supposed to be. Yes, it looks like that. So let's see. 80 minus, here it's going to be 60. Okay, 60 into cos 30, right? And then plus 4,83. So here you need to be very careful when you're doing these calculations. It can horrify the situation. So here we've got 23, comma, I'm going to make it to 3 decimals, so it's going to be 2085 is equal to 5,3a. You can make that one equation 1. You could have left it there even. So now we're going to consider the crate. What do we see? On the crate, there's just two forces acting. Is the tension upward and the gravitational force downward. Okay, so it always helps, guys, to identify, your working materials. So for the same reason, we know that the resultant force is equal to ma, which implies if we're going down Fg, again here you may choose a direction or you just work things as you know them. So this is Fg minus the tension equals ma. Fg is basically m, so it's basically 9,8 m because we don't know that mass, minus the tension, which is 80 newtons, is equal to m into a. Okay, great. So we can see that this becomes equation 2. Okay, now what we do here, we solve simultaneously. We can put 1 in 2. What do we get? We get 9,8 m minus 80. Okay, I think we're going to run into problems. we're supposed to solve for the acceleration there and not leave it like that, because without the acceleration it gives us a bit of a situation, is it not? Yeah. But anyway, I'm going to solve that problem. Let's just move stuff around. Let's just move stuff around a bit. Okay, so here we can make a conclusion and say therefore A is going to be, because we actually can calculate it, so it's 23,2085 divided by 5,3. So here it's going to be 4,37. Let's make it 9 meters per second squared to the right, is it not? Yes. And then we substitute here. We don't need an equation 1, therefore here it simply says we don't need equation 1, but we can call this one equation 1. I mean, still okay. It's still okay, but it's a value, so because we don't want to say too much. Okay guys, let's move on. So minus 8 equals m into, now we're going to put this 4,379. All right, so what do we see here? We've got like terms, so this implies that we have 9,8m minus 4,379m equals to transpose the 80. Okay, just work out some maths here. So 9,8 minus 4,379. Each time, guys, is starting to run away from us. We've got 5,421m equals 80. Therefore, our m is going to be 80 divided by 5,421. So this is 14,76 kgs. Okay, great stuff. So it may be wrong, it may be right, but at times you can just work with what you've got, but you can check it. The way to check it is to substitute into the equations that you got and see if everything balances out. Okay. But we don't have that time now, so we're scoring 5 marks here. So most likely to use Newton's second law of motion is kind of great, and to get the substitution there is kind of great, and to get the acceleration was kind of great. You're not gonna get a mark for this formula and for that substitution, but this particular step is important in the final answer. So that's how those 5 marks are scored. So let's do a 2.4. 2.4 says the block moves on the surface. Now I'm not too sure what do they mean by the block moves on the surface, which surface they're talking about. How would the frictional force on the block change? How would it change when we don't even know what they're talking about? So will it increase, decrease, or remain the same? At the end of the day, guys, I think we have a bit of a problem with this question. I don't know what is the answer here. It sounds ridiculous to me. Let's just move on. Question 3 says a ball of mass 0,2 kilograms, okay, is thrown vertically downwards, okay, from the top of a high building. The ball bounces from the floor, okay, so it will bounce. Great. Now the velocity versus time graph below shows the motion of the ball with the downward motion taken as positive. So please guys, be able to understand what is going on. So down is taken as positive. So of course our famous statement, ignore the effect of air friction, which is very important, because when it is not included, you could see on those MCQs how that can complicate our lives. Okay, let's move quickly. So we can see that, look, the velocity with which we projected this ball was 2 meters per second, right? And it reached the ground with a velocity of 9.6 meters per second, because we're throwing it down, and you can see an upward deflection on the graph means a downward motion, right? Right. And then as it hit the ground, you will see that it bounced off the ground with the velocity of 8 meters per second, the fact that it is negative, right? And then it goes on to reach maximum height, which is where the velocity is 0 at that time t, and then it goes further, but we don't know to what extent that is. So we have an understanding, but let's just draw a bit of this sketch here so that we can have a better understanding of what is going on here. Now we've got this ball right here. It is thrown down, hits the ground, okay? And then of course, as it hits the ground, it will then bounce back to some maximum height. And then there is the ball right at that particular maximum height, and then it starts moving back again. But now we don't know for the second motion, where does it go? So it helps to do the trajectory. It's very important. Now let's have a look. It says write down the magnitude of velocity. Okay, write down the magnitude of velocity with which the ball bounces from the floor. So it bounces from the floor at a velocity of 8 meters per second. So we're doing question 3 here. So we've got here 3.1. So basically the magnitude of the velocity, we know that it is going to be equal to 8 meters per second upwards. Of course, they didn't ask you the direction, they just said magnitude, so that's what you want. Okay, you get 1 mark there. 3.2 says write down the magnitude and direction of the acceleration of the ball at time t. We know that, well, the acceleration is basically the gradient in these graphs. You see, it is the gradient in these graphs. And since we are doing a free fall here, it's gravitational force. And by the way, these two should be parallel, right? To suggest that they're of the same gradient. So what we know is that the magnitude of the acceleration here, it's 9.8 meters per second. And then the direction is downward. Because gravitational acceleration is always downward. So here you're getting a mark for the direction and for the value. So 3.3 says, is the collision of the ball and the floor elastic or inelastic? Explain the answer with reference to the graph. Okay. Now, I like this portion here. So you're not going to say other things but what is on the graph, okay? So what do we see? We can see that it hit the ground with a velocity of 9.6 meters per second, but rose at a velocity much less than that. So that means we lost energy there, kinetic energy essentially. So this is definitely an inelastic. So we can say inelastic collision. Okay, and the reason is that the velocity with which the object hits the ground is more than the velocity with which it bounces off the ground. Okay, my writing is not good, but I'm sure you can follow. So that's what we can see. You can even include those magnitudes, but either way, you put it in a way that makes sense and you walk away with your 2 marks by choosing the type of collision and your explanation. So let's go for 3.4. It says now calculate, so this is where the action is. I'm tired, guys. My body is sore. I'm not exactly well. Got flu, but yeah, I'm trying to fight it. So I'm actually in bed doing this thing. Ish. But now I'm still stuck in these questions and I'm feeling like I'm burning. Okay, the height from where the ball was thrown. So we want that height. So this one is easy because basically we just want to focus on this portion of our triangle. Okay? We just want to focus on that portion and nothing else because that area will give us the height. So it's a triangle. You can use the triangle there if you like, but I'll just use equations of motion because nobody dictated how we're going to do this. So this is 3.4.1. All I know is that the final velocity squared equals initial velocity squared plus 2g delta y. Right, and I know I'm looking for delta y. So this implies that what is the final velocity is 9,6, and remember this is downward. So we took it as positive. Initial velocity was 2 squared plus 2 into 9,8 delta y. In fact, you can put h if you like. Let's just put h for just argument's sakes, because they told us it's the height h. We can say therefore h is going to be 9,8 squared minus 2 squared divide by 2 into 9,8. Okay, let's put it into the calculator. So 9,8, I win. Yo, guys, why are you quiet? That's not 9,8. That's 9,6. Yo. Mina niyathula nje nidla ushevu. Nidla ikhefu. Ngizotsha. So we've got 9,6 squared minus 4 basically. Divide by 2 into 9,8. Alright, so this becomes 4, comma, now when you do to 2 decimal places, it becomes 4,50 meters. Remember, we're told 2 decimal places. For me, I always try to leave it as it was given to me. So how many marks were you getting here? Standard 3 marks. Formula, substitution, answer. Height is a scalar quantity. No need to worry about other things. 3.4.2. Now we want the magnitude of the displacement. Remember, displacement is a vector quantity. Now of the ball, from the moment it was thrown until time t. So how is it displaced? Remember, the initial position is that height right there. The initial position is this height. Ish, guys, time is flying and I'm not happy with that. So the initial position is that height, h. Which we calculated right now. And then now the next position at time t is this position right here. Right? So which we don't know. We can call it delta y. We don't know that delta y, and therefore our resultant displacement is going to be this. That's what we want. Okay, so that is the question that we're being given. So we want the difference between these two. Okay, so let's start. Now we know that to find delta y is basically this area under that graph. Okay, and if we work out that area, we have sorted the problem. So let's first look at that particular spot, the maximum height that we get to. Okay, yeah, I'm trying to think. By the way, displacement is a vector, so we always take the we always take the final position and we subtract the initial position. Is it not so? It's always like that. But I'm trying to think what would be the best way. Remember, this displacement is upward against a downward positioned displacement. Anyway, let's just say the displacement here is going to be equal to that height h, right? It's going to be that height h plus. Remember, whenever you're adding vectors are actually additive, but depending on their directions, it becomes a bit of a situation. So let's call it delta y. You will have shown the sketch, right? You can see the sketch I'm working on. H is basically 4,50 plus. Now, what is delta y? Remember, delta y here, if we're looking at this formula, we don't know the time, so we have to use this formula. For delta y, here, we're going to use this formula. Final velocity squared equals initial velocity squared plus 2g delta y, right? And if we make delta y the subject of the formula, delta y is going to be that final velocity squared minus initial velocity squared divided by 2 into g, right? So that's what we want. So we're going to use, so I'm integrating now. So we're integrating now, guys. You're grade 12, so you should be able to follow. So this is basically this final velocity. Okay, let's just do this and show that this is a separate calculation. So we're going to have final velocity squared minus initial velocity squared divided by 2 into g. And then maybe I should not substitute as yet. Right, h. So then we substitute h, we got 4,50 plus this one is that final velocity is 0, right? Because at the maximum height it's going to be 0 minus the initial velocity, it was minus 8 squared. All of that divided by 2 into 9,8. So be cognizant of those directions, right? Right, so I'm just doing a quick calculation here. You can split it into steps, but I'm just trying to show you some, fine or cool ways of answering. You know, plus into. So here we've got 0 squared minus into minus 8 squared divide by 2 into 9 comma 8. So what I'm getting here, I'm getting an answer of 1 comma 2 4 to 2 decimal places meters. And then of course the displacement, you can see that we said downward is positive because actually this is being displaced downward from its initial position. So it came out nicely, and they just said magnitude, but we know that if it is positive, it is down. So please treat vectors with a bit of respect, okay? These are the elders of physical science. Again, guys, there's just more fancier ways to deal with things, but if you know what you know, it's already good. So you can get a mark for a formula of some kind. All right, and then you can get a mark for a substitution of some kind. That is general substitution. You're getting a mark for the final answer. So where are the 2 marks? Basically, the 2 marks come from these calculations here, because this would have been a separate calculation if you think about it. Or you can just simply say you want to calculate this separately, you get 3 marks, and then the final 2 marks is what you would do at the end. Either way, 5 marks in the bag. All right, let's move on. Next question says, draw a position time graph. Okay. For the complete motion of the ball from when it was thrown until maximum height was reached after the bounce. So meaning, basically, from our sketch, we want a graph that does this. So we just want this situation here up until there. We're cutting it there. Okay, not a problem. That's easy. That's easy. So 3.5. We will have our axes. Okay, let's first start. This is a position. Versus time graph of ball. So whenever you do a graph, you do this. But sometimes they provide you with a, they provide you with a graph paper to work with. So now that we don't have it, we'll just make our own thing, so we don't mind. So of course here on the x-axis, it's the time axis. Okay, and then here we're going to have position in meters. All right, and then what are they telling us? Use the flow. Why is on country? So use the flow as the 0 position. So if the flow is the 0 position, so what does that mean? It means exactly what it means. All right, so we displaced our graph positively. Now I'm trying to think, what is the story here? If we use the flow as 0 position, okay, let me think a bit. It says now clearly indicate the following on the graph: the height from which it was thrown, okay, and the time t. Okay, great. Only 2 things we have to show here. Now let's think about it. What happens to this ball? It is thrown from 4, right? And drops to the ground 0. So this is now the first one. That was 4, comma, what did we get? 5, 0. So it's basically 4,5 meters. All right. And then we threw this one. Remember, it follows a parabola or parabolic. It is parabolic. So this one is going to do stuff like that. Ne? Great. And then it reaches the ground, and then it spends a bit of time there when we dissipate, some energy there, which we don't know how long it is, but we just want to capture it, and then it goes to this maximum height. So there we know that we're looking at time t. Okay, and we were never asked to calculate anything else, so we've indicated that one, and then we need to also indicate this one, this height that we reach. It is 1. Oh no, I did not calculate it. So you see now the dangers of not doing that calculation is this one right here. So we've got -8 squared divided by 2 into 9,8. So sometimes the choice of integration can hurt you. So this is going to be 3,27, okay, meters. Of course, this is gotten from this calculation right here. So sometimes doing 2 steps separately makes life a lot easier, because then you don't run into the problems I am running into right now. Okay, so now we can draw a graph. Nice and easy. Okay, so there is our velocity time graph. So we're getting a mark for showing the height from which it was projected by showing that time t that we got to the second maximum height, and I think that second maximum height is an extra mark, and the shape of the graph is how you get those 4 marks. All right, so you can see these questions are a bit hectic, guys, so you need to make sure you know them. So it's coming back, so please watch the videos I have done even for your term 1 exams. Make sure you get the papers from all around the country for this year's term 1 exams and do them. You may just find yourselves a bonus, you may find yourselves a bonus, because you will find that some of the questions are going to be what will be created as your exams for your term 2 in a particular province by taking a question from another province and maybe sometimes modifying it a little bit. So be aware that there's not so many questions that these people know, but they just play around what they have available to themselves. So don't cheat yourself and do the right thing. Okay, let's try and move quickly. Now I told you a cricket ball of mass 0.15 kilograms is dropped. So when you drop it, what do we know? Initial velocity 0 from rest. Of course, they're giving too much now. From a height h, okay? It reaches the ground with a speed of 6.2 meters per second and is in contact with the ground for 0.2 seconds. So that is the impulse time. Now the ball bounces straight upwards with a speed of 3.62 meters per second. As you can see, it has lost some kinetic energy. Ignore the effects of air resistance as always. Okay, we've been given a sketch here, so we don't need to work out too much. So the question says define the term impulse. So you see, these are topics you make sure you don't play around. When you get a question on a definition, you get it right, please. An impulse is basically defined as the product, because you look at what are the units of impulses? Newton times second, isn't it? So it is the product It is the product of the force, the resultant force even, of the resultant force acting on an object. It is the product of the resultant force acting on an object and the duration and the time of its action. Let's just say and the time of the time of its duration. Let's not even say the same thing. The time of its action on the object. Okay, so you just think about certain things. Remember, you're not going to remember all of these things, properly. So you use certain clues. Sometimes when you cannot be sure, you ask yourself, what is the unit for impulse? It's Newton second, right? And then you just simply say that. Easy as that. You can just know from the unit how to work your way around. But I'm sure what is important is to know that it's the resultant force and the time duration of its action. If you say that, you are sorted. You should be getting your 2 marks and you smile. So 4.2, why am I jumping like that? 4.2 says calculate. So now this is action. The magnitude of the momentum of the ball when it reaches the ground. Simple. So 4.2.1. We know that momentum is mass multiplied by velocity. And then, of course, we're choosing downward as positive this time around. So 0.15 into the velocity with which it hit the ground was 6.2. Where's my calculator? Come on. 0.15 into 6.2. So this is 0.93. Now what are the units for momentum? It's kilogram times meter per second. And it is a vector, right? And a vector is downward. Great. So always when you do your final answer, it must have units. If you lack a unit, you are a dead person. Get a mark for the formula substitution, the answer with the units. An answer must have a unit. Okay, so that's easy. Of course, we chose downward as positive. So somewhere in your answering, you must indicate your choice of direction. Now 4.2 says the impulse on the cricket ball during the collision with the ground. Okay, so we know that, well, impulse F delta t is basically the object's change in momentum. Easy. This implies that F delta t is equal to, now what is the change in momentum? Is the mass into the final velocity minus, oh no squares there, minus the initial velocity, which is equal to the mass is 0.15 into the final velocity is 3, but it's directed upwards, so it's going to be minus 3.62 minus the initial velocity, which is 6.2. Okay, so let's go for it. So this is 0.15 into minus 3.62 minus 6.2. So I'm getting a minus 1.47. Of course, we're rounding off to 2 decimal places. So this is therefore equal to 1.47. Now this is Newton's seconds. Remember, this is a is it a vector? Because of Newton's, I think it's a vector. So but they only said magnitude. No, they didn't tell us magnitude. Ho 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 ho. Okay, let's just say upward. Yeah, it is negative, so it's upward. So sometimes think of the direction of what is happening there. Correct. It's good. I'm not sure. Is it a vector? Yeah, it's a vector. It is a vector because momentum is a vector. So change of momentum has direction. So yeah, we need to say the direction. So here we're getting 5 marks. Okay. What is the marks here? Formula, substitution, the magnitude, and I think direction is important here. So it's 1, 2, 3, 4. Where's the 5th mark? Perhaps the 5th mark is Perhaps the 5th mark comes from this. I'm not sure. Remember, this could have been a separate calculation which could give you 3 marks, okay? Because you'd have a formula, substitution, answer, and then you put it in here, plug it, and you get an answer. So probably something like that. But I'm moving on. So we're getting 4.2.3. It says now we want again the magnitude of the force that the ground exerts on the ball. Okay. Remember, the force in question is the resultant force. So if we draw a free body diagram on our object, it's going to experience a force upward. This is the force by the ground. And then it's going to have its weight. Okay? But now we can tell that the impulse is upward, so it means the resultant force is going to be upward. Okay? Since we could see that the product of the force and the time duration was essentially negative. So we know that the resultant force is upward. So if the resultant force is upward, it means that force by the ground is greater than the gravitational force. So of course, we know that we can use our impulse equation here and say F delta T is equal to change in momentum, right? This implies that the force is going to be the change in momentum over the change in time. So what is the change in momentum? The change in momentum is basically the impulse itself. So this is now minus, we're going to substitute it with the sign, minus 4,7 divided by the time duration. We were told it's 0,02. So that's the resultant force here that we want. So this is minus 1,5 47, which is in any case like that, divided by 0,02. So I'm getting here a 73,50 newtons, which we can interpret as 73,50 newtons upwards. But they only wanted the magnitude. So that is the story. Again, formula, substitution here, and the answer. Now I'm trying to figure out, guys, why would you get 5 marks here? Oh yeah, this is the resultant force. This is the resultant force. As you know, technically that's the resultant force. Now we want the force by the ground. So you see, sometimes looking at the marks will help you to not mess up. So we can say this then implies, I don't know, we say then, this implies that our resultant force is equal to the force by the ground minus, or you can say plus, depending on the signs that we choose now, minus the force of gravity, right? Because everything was directed upward, so it means that force is greater than gravity, because this came out as negative and we saw that negative was upward. So which implies, what is our resultant force? Our resultant force is this 73. Remember, this is upward, so it's negative. So I don't know how we're going to deal with this now. We need to be smart about it. We know that vectors actually add to try and avoid problems. So this is basically going to be minus 73,50 equals this F by the ground plus the gravitational force is basically, what is the mass of this object? It's 0,15 into 9,8. So therefore, the F by the ground is going to be minus 73, 50. I don't know why I did that, yeah, but it's fine. Let's just move on, guys. You will adjust for that. This is an intermediate answer. I thought it was final, so it's an intermediate answer, so you don't round off like that, but let's just move on. It came out like that anyway. Minus 0,15 into 9,8, isn't it? So let's see. Minus 73,50 plus, minus 0,15 into 9,8. It gives us a 74,97 newtons. Now remember, this is now 4,97 newtons upwards. So please, guys, make sure you are well orientated and you understand the science, because sometimes you will get clues as to why things are the way they are. So here they only wanted magnitude, so this is the fourth mark, and the fifth mark is actually this substitution over there. Great. So these questions are a little bit hot. They're a little bit hot. And then it says prove. I mean, they meant prove, not proof. So it is supposed to be prove by means of a calculation that it is an inelastic collision. Okay. I mean, that one is just free marks, free marks. So let's do a sun papel. 4.3 says here, we want to prove, so we can just say sum of EK before collision is half mv squared. Remember, it's just a single object. So this is 0,5 into 0,15 into the initial velocity was 6,2 squared. So basically 0,5 into 0,15 into 6,2. So we're getting a 0,46. I didn't square that here when that 0,5 into 0,15 into 6,2 squared. So this answer is not true. So the answer is 2,883 joules. Okay, and then the sum of EK after collision, again, is the same object. So this is 0,5 into 0,15 into minus 3,62 squared. Ish. Things keep getting touched and I have no control of it. So minus 3,62 squared I'm getting a 0.983 joules. So we can see that which is not equal to the sum of EK before. Therefore, the collision is inelastic since sum of EK is not conserved. Sorry for the writing, folks. I am a bit agitated now because this thing is taking forever. So either way, you're getting a mark for that calculation, and here you're getting a mark for that answer and for your final conclusion, basically. Nice. Calculate the percentage of the kinetic energy that is transferred to other forms. So this is a nice question. You don't get it that often. So 4.3. So if we want the percentage, we know that the percentage EK transferred is going to be equal to the final EK minus the initial EK. Then we divide all of that by 100. No. Is it by 100? No, we divide by the initial EK. Of course, I'm just trying to make a bit of a formula here so that you can follow, but you know the procedure. What was the final here? It is 0.983 minus the initial was 2.883. All of it divided by the initial, which is 2.883 times 100%. So easy stuff. 0.9. Because these are scalar quantities, man, we don't even need to do this one. This formula must be adjusted a bit. It's going to cause me problems. So we're going to say EK final minus EK initial. Why am I repeating this thing? Remember, we're taking from the initial and we're taking that final. So man. Now this thing is just doing me a number. So this one is 2.883 minus 0.983. All of that divided by 2.883. Yes. Okay, 2.883 minus 0.983. Is that one? Then we divide by 2.883 and then we multiply by 100. So I'm getting a 65.90%. Okay, so I mean, you could become skilled and pretend you're doing some mathematical calculation so that it makes sense. And then, yeah, you do your things. So you're getting 4 marks here for this calculation. So I'd say to make up some sort of a formula, it's great. For this difference on top, it's important. And then for the rest of the general substitution and the answer, that's how you score those 4 marks. Okay, guys, there we are. So let's move on to question 5. Okay, now we have an hour to dance here, so let's be quick, guys. We've got to be quick. Now let's see. Question 5 says a steel ball of mass 5 kilograms is connected by a string and swings from rest. Rest means initial velocity is 0 at point A. As the steel ball swings through the lowest position at point B, it collides with the stationary block. Okay, stationary block also meaning its initial velocity is also 0 of mass 2 kilograms. Okay, not a problem. Let's try to move now. Immediately after collision, the block moves with a speed of 4.95 meters per second to the right, okay, on a frictionless track BC, meaning it moves forever. After the collision, the steel ball swings to a maximum height. Okay, not a problem. Ignore effects of friction and assume that there is no loss of mechanical energy. Okay, that's a closed system right there. So we've got our diagram there for us, so it makes life easy. So it says now explain what is meant by an isolated system as used in physics. So we're doing question 5. 5.1, what do we know? An isolated system is what? We can just say it's a system in which there is no resultant force. Sometimes I don't like this part because it doesn't make sense. But in any case, that's what it means. It means the resultant force is 0. So that is the definition of an isolated system. Let's just forget the complications. Okay? Great. Easy 2 marks. So guys, definitions, always revise them. There's no point in missing marks because of wrong definitions. But like I always say, for you to understand a particular definition easily so that you don't mess up, you need to understand its implications. Now it says calculate the velocity of the steel ball immediately after collision. So you can see here there is a little bit of sweating going on. 7 marks, you're not going to be playing here. First of all, we can see that there is a bit of momentum here, and then of course mechanical energy in an isolated system. So first of all, we need to know the velocity of the steel ball before this thing happens. So we can say velocity of ball before collision. So what do we do here? Before collision, what happens to this? We know that potential energy at the top is equal to the kinetic energy at the bottom. That's the law of conservation of mechanical energy. As you can see, at the top it's stationary, so there's no kinetic energy. So I'm not going to waste my time writing a complicated formula here. As long as it's going to get me the right answers, no one is going to say anything. If they try, they're going to get it, and they're going to get it good. Okay, let's go on. This implies that mgh is equal to half mv squared. And remember, this therefore implies that our velocity is going to be the square root of 2gh. Remember, when you cross multiply by 2, there you get 2 mgh. You divide by m cancels out, so you get 2gh. You take the square root. That is what happens. So I'm moving quick with my gymnastics. Therefore, v is going to be the square root of 2 into 9,8 into the height there was 1,2. Okay, we need that velocity. We need that velocity. So this is going to be the square root of 2 into 9, 8 into 1, 2. So I'm getting a velocity of 4, 8. Remember here, you don't round off too soon. 8. This one says 85 by 4, see? Yeah, it's going to be 850 meters per second. And then, of course, by the time it reaches at point B, it's going to the right, right? Yes. So that is what helps us to get portions of this. And now we can say then, what do we know? We know that the sum of momentum before is equal to the sum of momentum after collision. Okay? This implies here we've got the mass of the ball. Let's just say MB. I don't know what we're going to do. MB of the ball. And then the initial velocity of the ball plus the M of the block again. I don't know what we're going to use block. We can use capital letter B times the initial velocity is going to be equal to MB and its final velocity plus the M of the block and its final velocity. Right. This implies what is the mass of the ball is 5. The initial velocity, it was at rest. No, it's not at rest, but it's this one. It's 4,850. Plus, this block was stationary initially, so this is 2 into 0 equals, this one is 5 into what we don't know. Plus, this one is 2 into the final velocity. They gave it to us and said it was 9. It was 4,95. Okay. Therefore, the final velocity of the ball is going to be this one, 5 into 4,850 minus, we transpose this 2 into 4,95, and then we're going to divide by the mass of that object, which is 5. So sometimes when you create a bit of a situation for yourself, it helps you to clear up problems. 4,80 850 minus 2 into 4,95. But some calculations cause you a bit of pain and your concentration can lapse and you may run into problems. So I'm getting 2,87 meters per second. And then this is going to be to the right, isn't it? Because here they just said velocity, so meaning we need to also consider direction. And don't forget, every time you do a calculation, the units have to come out. So now what did we do here? We did principle of conservation of mechanical energy. We can get substitution and that intermediate answer. But because now this is a different story, principle of conservation of linear momentum, and then substitution, and then the answer. It's how many marks? 1, 2, 3, 4, 5, 6. And then the 7th mark is for the direction. If you miss it, you are a dead individual. Okay, let's move on. We're getting to 5.2.3. It says now, no, not yet. 2. Okay, it says now the height h reached by the steel ball. Again, they told us it's a maximum height. So technically, we're doing, again, principle of mechanical energy. So I'm just going to say EK bottom is equal to EP top. Because there's nothing else. Maximum height means velocity is 0. Okay? So that is the story. So I don't want a complicated calculation. So when you know what you're doing, nobody's going to push you around. So this is half mv squared is equal to mgh. So if I want h, what happens here? I just divide by mg. If I divide by mg, so what is the story here? I'm going to have half mv squared divided by mg. And then that guy cancels out. So I have 0.5 into the velocity there. The velocity is the initial velocity, by the way. What is that initial velocity? We calculated it's 2.87 and then it's squared. Divide by g, which is 9.8. How? So we've got here 0.5 into 2.87 squared divided by 9.8. So I'm getting a 0.42 meters. All right, so that is it. So sometimes you just think about what you need to do and you just do what you have to do. Isn't it great? It is definitely great. So easy stuff here. Again here, they were just on a mark giving spree because I think this is 3 marks, guys. So this is 3 marks in my opinion, but you're getting 4 marks, and I believe the 4 marks therefore is perhaps knowing that the velocity to substitute there is that one, I suppose. Or you can say 2 marks for the answer. It's okay. Okay guys, let's move on. 5, I'm feeling tired. 5.2.3. Yes, we need to move, guys. Hey, time is really not on our side. It says now the time for the block from the moment it started to move to reach point C. And what do we know about that? It is 12 meters from point B. Okay. So what do we know here? We use equations of motion. We know that delta x is equal to the initial velocity times delta t plus half acceleration times delta t squared. I really hate these delta businesses. And then we know that we are told here that this is 12 meters is equal to the initial velocity. We know now that this is that velocity that it left with. So it was what again? 4.95 times delta t plus this one is 0. By the way, the acceleration is 0 because it was doing constant velocity. So that one falls away. Therefore, we know that our delta t is going to be essentially 12 divided by 4.95. All right, let's do it. Can't see now, it's dark here. Divide by 4.95. So I'm getting 2.42 seconds. Okay, so that is great. Again, equation, substitution, answer. Time is a scalar quantity, so nothing big there. All right, let's move on. Now we are told here the block moves from point C with the speed, cause you see we did constant velocity there, although we had to assume it. Okay, it moves up a rough inclined plane to point D, okay, which is 0.6 meters above the horizontal, as shown in the diagram below. Okay, the diagram is everything that we want. So it says state work energy principle. Now that's something for you to go and make sure you have revised. Okay, so the work energy theorem basically states that the total work done on an object is equal to the object's change in kinetic energy. Okay, that's it. So easy stuff, 2 marks for free there. But make sure you understand that thing so that it doesn't haunt you when some serious questions are being posed. Now it says, now the block reaches point D with a speed of 2 meters per second. Now we are told what to use using energy principles, so nothing else. So you cannot use equations of motion alone. Calculate the work done by friction. Friction is a non-conservative force when the 2 kg block moves from point C to point D. So it's a non-conservative force, so we know that work done by non-conservative force is equal to the change in potential energy plus the change in kinetic energy. Easy stuff. Therefore, we say this is implying that work done by friction here is going to be equal to M into, not M, but mg into the final height minus initial height plus half m to final velocity squared minus initial velocity squared. This one can get a bit hectic. So what is the mass of this object is 2 into 9,8 into, what is the height there? Basically the final height is this 0,6 minus initial, there was no height, so it's 0, plus half, maybe let's just write 0,5 instead. The mass is 2. Then the final velocity there was 2 meters per second minus the initial velocity here was 4,95 squared. So the calculation is getting a little bit hectic. Okay, I need a bit of light here. Let's just pause for a second. Okay guys, I've got my lights on, so let's do that calculation. I'm getting a value of minus 8,74 joules. Okay, so remember it's negative, and that makes sense because friction is opposing the direction of motion. So we can just summarize that and say it's just 8,74 joules because it's a scalar quantity. We don't worry too much about other things. The sign only is trying to make the sense of the situation, that it's not doing positive work, but it's actually doing negative work. Easy. So they're giving 4 marks. Formula. So perhaps each substitution here, because it's quite complicated, and the final answer. Okay, so you can see this question was made a little bit interesting. So let's move. Question 6. So we're told here, question 6, so we're doing Doppler effect. So these are the topics for your term 2. An ambulance moves at a constant speed. Okay, what does that mean? The resultant force is 0, and therefore there is no acceleration as well. Along a straight horizontal road towards a stationary listener. So the velocity of the listener is 0. So we know that here VL is 0, but the velocity of the source is some value x if we choose. Now the listener measures a frequency that is 20% more than the frequency of the sound emitted by the siren on the ambulance. So what does that mean? It means our frequency of the listener is basically going to be 20 over 100 of whatever value y that frequency is. Let's just say the frequency of the source is y. So it's going to be that plus, because they said 20 more than the frequency that was emitted. So it's going to be the 20% of that value plus its value again. So that means the frequency of the listener is like that. And then that is the story. So please make sure you understand statements that are given to you, because they always try to trick you. 6.1, easy, Doppler effect in words. The Doppler effect is defined as the apparent change in the emitted frequency by a sound source as observed or detected by a listener. Okay, so it is the apparent change in the emitted sound frequency, or in the emitted frequency of sound. In the emitted frequency of sound. By a sound source, or we can say by a source as detected by a listener when the sound source and listener move relative to each other. Okay, please guys know these things. So some definitions can be a bit wordy, they have a lot of words, but it's an apparent change. That's what matters. In the frequency of a sound source, by a sound source as detected by a listener when the sound source and the listener move relative to each other, because there has to be some movement in relation to one another. So that's how you scoop the 2 marks. Okay, let's move on. So we've got here 6.2. It says calculate the speed of the ambulance. Take the speed of sound in air to be 340. So you need to know that by heart, because we are sometimes not given that. So you just need to make sure you keep it in mind. But whatever value they volunteer for you, you use it, irrespective of what you know. So we need the Doppler effect equation. So it says the frequency of the listener is equal to the velocity of sound in air plus or minus. In fact, this one is in a particular medium, not necessarily air. The velocity of the listener divided by the velocity of sound in a particular medium plus or minus the velocity of the source multiplied by the frequency of the source. Great stuff. So this implies, now what is the frequency of the listener? They said it's 20% of the stuff that we know. So technically, we're going to do stuff like this. We're going to say, look, we've got here 20 over 100, okay, of y. Okay, maybe we can just not even put too many brackets. So y plus y. Ne? We decided we're going to use those. Whatever you use is up to you guys. Equals, this is 340. But now the listener was stationary, so we forget about that. The focus now is 340. Remember, when you're going towards a stationary source, it's going to be negative because we are trying to get some improper value here to give this one a bigger value. Okay, so this is what we want. So what did we call it? We called it x. So I mean, let's just say Vs to avoid confusing people. And then here the frequency of the source, we decided it's y. Okay, great. So if we divide by y throughout, what happens? The y's disappear. So this implies that we've got, so if we divide by y throughout, because y is common everywhere, so it is such that we're going to have 20 over 100 plus 1 equals 340 divided by 340 minus Vs. Okay, which we can continue here. So the gymnastics that we need is going to be 340 minus Vs into 20 over 100 plus 1 equals 340, right? That is the gymnastics we're going to end up with. Oh, by the way, yeah, that's what it is, because that whole thing is over 1, isn't it? Yeah. And then what do? The thing that we do, we just divide by that. So we're going to have here 340 minus Vs is equal to 340 divided by that. All right, so we are getting where we want to be. So what do we know? Let's just try and see if we can get a nice value here. 340 divided by 20 over 100 plus 1. Yo, I'm getting a nasty value, but anyway, let's just write it as it comes. 850 over 3 is 340 minus Vs. Okay, we're just dragging a little bit. Therefore, what do we know? Vs you transpose this to the side, and then it's going to be 340 minus 850 over 3. Trying to not have a problem here. So we're going to have 340 minus 850 divided by 3. So it gives us a 56, comma, in the forward direction. But of course the question was that do speed. So speed is a scalar quantity, so there's no need for direction. Okay, so that one needed you to be a bit crafty. Okay, you needed to be a bit crafty to do it. But again, the Doppler effect equation is good, or the Doppler equation if you want. And then we can simply say the substitution there is good. And I think this was a smart way to show things, so you would probably deserve a mark for it. And then the answer. So the rest was maths that you need to know. You cannot say you have no gymnastics. If you're doing physical science, your maths gymnastics are a crucial thing. Okay, let's quickly finish this question. Now it says, how does the frequency of the listener. Okay, how does the frequency the listener hears at point P compare to the frequency of the siren when the ambulance is at point P? So remember, at point P, everything feels the same because that one is going to be actually equal to. Okay, this one is a simple question. So 6.3, it is equal to, because at P, that guy will hear exactly what is being emitted because it's as if that is stationary for that moment it passes him. So you get your 1 mark and you move on. Yeah, things are getting touched and it's irritating me. Okay guys, let's try and make up some time and see if we can, if we can. Let's just do it. Do we have we have a lot of questions. Okay, let's try to move quick. Question 7 says 3-point charges X, Y, and Z are arranged as shown in the diagram below. Okay, the charges on X and Y are, because we've got here -2 nanocoulombs and a +6 nanocoulombs respectively. Now the point Y experiences a resultant force of 5 times 10 to the -3 newtons in the direction of 32 degrees. So again, this is critical stuff that we need to not mess up. Okay, west of the line. Remember, that direction is very important. We're dealing with vectors here. West of the line YZ. So if we're doing that, we're trying to suggest that the resultant force is in this direction. So this is the resultant force of the electrostatic force. Okay, and if we're saying 32 west, it means this becomes the 0 line. So we measure our 32 degrees in this direction because that would be west of north. Okay, great. That is the most important. So it means this charge would move in that direction if it were to move. Okay, all right, okay. Now we're told state Coulomb's law. I think, guys, I don't want to do it now. Okay, I don't want to do it. But yeah, let's not be silly. Let's just show you the things. So Coulomb's law says the electrostatic force between 2 point charges is directly proportional to the product of the charges and is inversely proportional to the square of the distance between them. Okay, so again, this is something you need to make sure you don't go into any exam not knowing. Okay, definitions are easy marks. 7.2, we're told to draw a labeled free body diagram to show the electrostatic forces on point charge Y due to the point charges X and Z. Also indicate the net force on the point charges. Easy, we've got it there. So we know that if we say this is our Y, remember positive and negative charges, they attract, so it will experience a force in that direction. Let's just show it nicely. So this charge Y will be pulled in that direction by X. Okay, so what do we know? We know we're going to have here a force in that direction. So this force, we can say it's Fe of x on y. Okay, so it's x on y, right? And then we have this one going straight down, right? But now we know that this is a positive charge and it's a positive charge. So y will actually be experiencing a force in that direction, you know, because due to z, wait, z is not positive. Z is not positive. We need to determine that. Remember, if the resultant force is going that way, it means the force in here is directed down as well, because that would mean we are getting a parallelogram method for the resultant force, okay? Or if you shift one of the forces, it's a head to tail method. So that means for this to be the resultant force, Z should be pulling that charge as well. The electrostatic force is directed to Z. So it's like that. So that was the tricky part, I guess. This is the electrostatic force of Z on Y. Okay? And then, of course, we saw that the resultant force is in that direction. Okay, that's the resultant force. You can even write its magnitude. It's not a big deal. So that's what we've got. Great. Easy 3 marks there, because it's just those forces. Okay, so you can write the names in full here, because I don't think there's a particular notation that is acceptable unless I don't remember something. But either way, your teachers have done a great job in teaching you something. Now it says, what is the nature of the charge? On Z. Remember, for the resultant force to go in that direction, Z has to be applying a force towards itself on that point charge Y. And the only way that force can go that way is if this is negative, because opposites attract, isn't it? Yeah, it has to be negative. So the answer is, it is negative. Okay, get an easy mark there. Yo, yeah, my fitting is on Olela. This thing keeps on blinking. Okay, let's try and move a bit. Let's just try and move a bit. So the next question says calculate. So this is where the action is, the danger. The danger. Now it says the magnitude of the force that point charge X exerts on Y. Okay, so remember, when we do a tail to head method on our diagram, I need you to notice something. Remember, let's just work on our diagram here. If we shift that force to here, this would be the same as Fe of X on Y, which is what they want. But we also know that that direction is at 32 degrees, right? Like that. And we know that this is going to be at right angles like that. So we have a right angled triangle. So we want this force, which is the opposite in that triangle. So we know that if we say, oops, not U. So if we say sine, because what are we saying? Charge X on Y. So that's the horizontal force. So if we say sine 32 degrees in this triangle here, what is that? The opposite side is Fe of X on Y divided by the electrostatic force, which is the resultant, right? So therefore our Fe of X on Y is going to be the Fe resultant multiplied by sine of 32 degrees. we were given that magnitude of that force. It was given to us as 5 times 10 to the minus 3 times sine 32 degrees. Okay, so let's see. So this is 5 to the minus 3 into sine of 32 degrees. So this gives us a 2 comma to 2 decimal places. It's going to be 6.5 times 10 to the minus 3 newtons. Remember, this is a force, so it's newtons. Again, they just said magnitude, but I treat this as vectors. This is to the left because that is x on y. So of course, trig ratios, substitution, and the answer. Easy 2 marks. Now let's do 7.4.2. Okay, this was 7.4.1, where we were dealing with 7.4. Okay. Now what is the story? It says the charge on Z. Okay. That's all right. So if we want the charge on Z, it means we need to find the force here. So we need to find that force. 2, we also need to find that distance, because we need 2 things here. I don't know why it's 5 marks. It should be more, because we need R so that we can use this R, and we need this force so that we can use that force. But this is easy because we can start with R. For us to find R, we need to use the above information. We need to use X. So we saw that, well, Fe x on y was given by, it's going to be the charge on x. So by the way, it's going to be Coulomb's constant times charge on x times charge on y divided by r squared, isn't it? This implies that 5 times 10 to the minus 3 is equal to 9 times 10 to the 9. That one was minus 2 times 10 to the minus 9 into 6 times 10 to the minus 9 over r squared. So what do we know? Therefore, our r squared, we want r. So our r is going to be the square root of whatever is going on in there. So the best gymnastic to perform is to say square root of 5 times 10 to the exponent minus 3 divided by this product here, which is going to be 9 to the 9 into the 2 to the minus 9 into the 6 times 10 to the minus 9. All right. So the distance that I'm getting here is 2, 1, 5. Why is this r strange though? Huh? Did I do something wrong? Yeah, I did something wrong. My calculation was wrong. It looks too big. Scaring me, but of course it may be correct, cares, but actually you cross multiply r, so you divide by that in that. So this is the square root of 9 to the 9 into 2 times 10 to the minus 9 into 6 times 10 to the minus 9 divide by this 5 times 10 to the minus 3. So I actually swapped the values around. Yeah, that looks a bit convincing. So this is 4,6. Now we're going to make it to 3 decimal places. 648 times 10 to the minus 3 meters. Okay, that's the distance. That's the first thing that we want. Okay, so we've got that distance, and then now we can say then what? we want that electrostatic force between y and z. So we know that Fe of z on y is equal to, but remember, we want to be skilled. We're using this triangle here. Remember that force is on the adjacent side in that triangle, so we can use cos. Is going to be basically Fe resultant times cos of 32 degrees. So I'm already moving fast, guys, to avoid a waste of time. So you know what is going on in there now. So we need this force. We do 5 times 10 to the exponent minus 3 into cos of 32 degrees. Gives us a 4,240 times 10 to the minus 3 newtons. Okay, and you know that that one is straight down. Of course, it's not necessary at this point. Now that we know this force, what can we say this implies? We know that this implies. How do we do the electrostatic force in general? We know that the electrostatic force is going to be we know that this is basically K times Q1, which is, now we can say, times QZ, which is what we want, times QY all over R squared. Now R squared in this case, okay, let's just write R squared is equal to 4,240 times 10 to the minus 3, right? Because that's the value of that electrostatic force, but now we're defining it in terms of Coulomb's law. This implies that 9 times 10 to the 9 into QZ, which is what we want. Okay, maybe let's just not do it like that. It's fine. Into 6, right? QY was 6 times 10 to the minus 9 all over. But now remember, the R here is halved, so this is half of that value we calculated, which is now 4,648 times 10 to the minus 3. You're in a hurry, Papa. And then that is squared, is equal to 4,240 times 10 to the minus 3. Yeah. Yay, and nansi into. Of course, you know from here now that the gymnastics that this is over 1, and then when you cross multiply here into your thingies, so we can see that therefore Q on Z is going to be, now this is 4,240 times 10 to the minus 3 into this half of 4,648 times 10 to the minus 3 squared, divide by 9 times 10 to the 9 into 6 times 10 to the minus 9. Okay, so yeah, you try to simplify your work a bit to make it easy. I don't know, man, this thing was like horrible. 5 marks for so much work. Anyway, let's go for it. We've got 4,240 times 10 to the minus 3 into a half, which is 0,5, into 4,648 times 10 to the minus 3, and then we square that one, divide by 9 times 10 to the 9 into 6 to the minus 9. Oof. Yeah, here there's a room for errors, guys. If it goes out of control, you will have the memos to go and look at, right? Now to 2 decimal places, this is 24 times 10 to the minus 10 coulombs. Okay, now it makes me a bit worried that this answer may be wrong, because I was expecting a nanocoulomb, but now I'm getting to the minus 10. Okay, but either way, let's leave it. Now let's see. That was 5 marks, Yane. A horrible calculation had to be done here. So first we needed this guy, 1 mark for it, and we also needed to determine this guy. Maybe we can give each other here 2 marks. Sorry for that, because it's 1, 2, 3, and then here we can give a mark for a substitution and for the answer. So that is how you could get those 5 marks. Great, so we are out of time, guys, but I think we are not so far away from the end. So if you're doing this and with the experience necessary to handle this, you should actually have no problems. So question 8. So what is that? Question 8 says, a charge N has an excess of 6 times 10 to the 6 electrons. Now a charge M of 6 times 10 to the minus 12 coulombs is placed 0.3 meters to the left of charge N. So we've got the diagram right there. Now it says define the term electric field. Again, this is something to make sure you don't go into any exams. In fact, for your term, For your term 2 exams, make sure you know all the definitions involved in each section of the materials you have gone through from your term 1 to term 2. Make sure that is the case, because that's where you're going to get yourself the cushion. So we want to define an electric field. This is defined as, what can we say? It's a space around a charged particle in which a positive charge let's say it's a space around a charged particle in which a positive charge will experience an electrostatic force. Okay, again, don't focus too much on my definitions. I'm just using my understanding and my own words as best as possible, because that's how we were taught. We were taught to use our own words, because that made everyone understand that we actually understood the material. When you regurgitate, it's easy to think someone understands when they actually don't. So that's why I don't really support the idea of you guys copying things as they are on your exam guidelines. But for safety, because at the same time you don't want to be too overzealous, do your own thing, and then you don't keep the science and then you lose it. So the key was use your own words to express the same idea fully. That's all. But again, there's plenty of definitions, some concise, some long, but as long as it makes scientific sense. So that's the story. So it is a space around a charged particle in which a positive charge placed at a particular point will experience an electrostatic force. You can say that, but yeah, you got the idea, man. You will have your books for refreshing that There's no need to make it too perfect. Now it says draw an electrical field pattern around charge M only. So we know that charge M is a positive charge. So we know that the field lines always move away from the center of the charge. So I'm not going to do a very complete thing here. So I'm just going to do something that makes life a lot easier for me. We can make it a lot harder. So we know that the field lines, because this is a vector, we have to show the directions at different points around it. So that is it. That is it. So you get your marks. I guess for the field lines it's a mark, and for knowing that this is a positive charge you get another mark, perhaps, but it would be 1 mark in my opinion. 8.3, it says calculate the nature and magnitude of charge on N. So we know that charge on N, it is going to be the number of electrons involved, right? What is that? This is now 6 times 10 to the exponent 6. And then the charge on an electron is minus 1,6 times 10 to the minus 19 coulombs. Okay, let's do it. Okay, maybe number of electrons in excess. You can write that. I mean, it's not a big deal. So this is 6 times 10 to the 6 into minus 1,6 times 10 to the minus 19. So this gives us a minus 9,6 times 10 to the minus 13 coulombs. So yay! It's a very rough situation. Why is it not 12? Why 13? Did I do the right thing? 6 times 10 to the exponent 6 into minus 1,6 times 10 to the minus 19. Sometimes, okay, it maintains the minus 13 coulombs, it's fine. Sometimes it gets you scared when you get an answer that is different from what you were given, but either way, they can do it on purpose. Now the next question says, calculate the magnitude of the net electric field, at point P. So we want the electric field at P. So this is an easy question. So what do we know? We know that the electric field at P is going to be the electric field according to charge P, according to charge M at P, plus the electric field according to charge N at point P. Okay, that's what we know. Okay, we move on. So we use Coulomb's law here. It's going to be KQM over R squared plus KQN over R squared. So this is 9 times 10 to the 9 into the charge on M is 6 times 10 to the minus 12. Okay, this is already positive, so I leave it as it is. Now the distance here is going to be 0,3 plus 0,1, then we're squaring it. Plus, this one is going to be 9 times 10 to the 9 into, I always like to use the sign as it came out here. This is minus 9,6 times 10 to the minus 13. That one helps me to get the direction right instead of struggling. So this is going to be 0,1 squared. Obviously, this answer is going to be negative, right? To suggest that the net field here is towards the charge N, because it is closer and it has a greater magnitude for getting the sign. Okay, let's do it. So we've got 9 to the 9 into 6 times 10 to the minus 12. Divide by 0,4 squared. plus, we've got 9 to the 9 into minus 9,6 to the exponent minus 13. That one divide by just 0,1 squared. So the answer here is a hectic one. It's minus 0,5 to 2 decimal places is 5.3. Remember, this is newtons per coulomb. And then, remember, they just said the magnitude, so it did not need the direction. But you are a physics student. Remember, when you deal with a vector, you must always include direction. You're not going to get an extra mark when the question dictated otherwise, but yeah, that is the impression or the idea. So you get a mark for this formula that you created for yourself, then for each calculation because it's significant. And then you get the mark for the final answer. And don't forget, always there has to be a unit. You can say 2 marks for the final answer, or you can get a mark for that calculation because that was a bit more complex than the other. Nice. This one is always easy marks. So let's do question 9. Of course, you would be told your time is up. So, but I mean, it's only because I'm taking the liberty to explain a thing or two. Now I told you an experiment. So there'll always be a question based on an experiment. It can be from any topic of the topics you've done. So be ready to get a question like that. In an experiment, learners use the circuit diagram shown below to determine the resistance of an unknown resistor R. Normally, resistor R is the internal resistance, isn't it? Tenda balaga bingo when so this is internal resistance, but you can put it inside parentheses because you're not too sure, because this might be a resistor in the external circuit. But let's find out what is going on here. Okay, there's the circuit. We can see the battery. Always we know that that would be the positive terminal and that would be the negative terminal. So what you call the current, or yeah, conventional current, moves from the positive all across the circuit. And then of course we know that this one goes like this because no current passes through here. It's a voltmeter. It's always a high resistance thingy. Okay, so it goes through here. This is a rheostat, or we call an adjustable resistor. So sometimes it's called a rheostat. Okay, it's an adjustable resistor. Then we go on like that, and then we're going to go through that resistor and back into the battery. Okay, now let's see. It says now the circuit diagram consists of a cell with EMF E and a resistor R. What? The cell. So if the cell has a resistance R, it means that's the internal resistance. So we were correct. Okay, a voltmeter is connected over a variable resistor. A variable resistor is the rheostat that can be set to to known values. Okay, meaning we can choose any values that we want. Okay, now the equation that is used by the learners is what the hell? What is that, guys? Yo. So the equation used is scary, is it not? Because now that doesn't make sense, does it? How did we get there? So it's always important to investigate whatever you are given. First of all, we're only told about the EMF and the external voltage. So we know that EMF E is always equal to the external voltage plus the lost volts, is it not? Which will tell us the external voltage is that V plus, and let's see now, plus the internal voltage, okay, which is, okay, now let's try to show this one nicely. Let's show this one nicely. The V external is going to be the total current multiplied by the total resistance of the external circuit, and that one is just the rheostat R, plus here is the total current multiplied by the internal resistance R. Okay, so that is what we've got. So now how do we end up there? If we say we divide by E, the EMF, it will be such that this is 1 equals, this is I tot, multiplied by R of the rheostat, then we divide by E, plus we've got I tot multiplied by R over that guy. So that is the first step. So it doesn't look anything like what we've got. But what we're happy about is that we've got the 1. We've got the 1 that is in there. And we've got our EMF on the denominator. So what is the next step? Whatever you do in maths, you can repeat it as many times as you want. Let's say, for example, we divide by the current, because we can see there's no current in there. So if we divide by current, okay, let's divide by the current multiplied by this R, because that R is on the denominator. So if you multiply by, we divide by that, things are going to be such that we've got here 1 over I tot multiplied by R of the rheostat equals, so when we divide by that, we only end up with 1 over E, plus when we divide by that dude here, we're going to get here I tot times R divided by I tot times R times E, and then these guys cancel. Therefore, the equation we end up with is 1 over, what is I tot multiplied by R is the external voltage, which is V. This one we can just rearrange. It's going to be R over this EMF multiplied by the resistance of the rheostat plus 1 over E. Voila. So you need to know about maths. You see, if you keep your mathematical gymnastics in order, you will know how we got there. But sometimes it looks scary. Of course, you will decide if you want to waste time to look at that. But now, why did I do all of this? This already tells me that I'm using Ohm's law, nothing else. Because this helps to understand, because look, this formula is based on Ohm's law, right? This formula is always based on Ohm's law. So technically, this formula here still uses Ohm's law, where the resistance is directly proportional to the voltage, where the resistance, where the current is directly proportional to the voltage, provided we keep the temperature constant, meaning the resistance in a way. Great. So now we are ready to hustle this experiment, because it looked as if they're doing gibberish, but now we understand what that is. So now let's see, we've got a y-intercept here, right? And we've got the gradient to the slope. So now in this formula, we need to understand what is what. And then of course, we've got these points here. We've got those points right there. And thankfully, they all fall onto a particular line. Makes life a lot easier. Now, what do we know? Look, 1 over V here is put on the y-axis, right? As you can see there. And then we've got 1 over r is put on the x-axis, okay? So 1 over r is basically a different story. So 1 over r somehow is put on the x, because there's an invisible one there. It's on the x-axis, meaning it's a variable. And then this is a constant. We normally would call it a c. So can you see this is a linear equation, y equals mx plus c. So meaning the y-intercept is 1 over the EMF. The gradient is basically going to be r over E, because those two are constant. Remember, internal resistance is constant, the EMF is constant. This is variable. That is why it becomes on the x-axis. So we can understand that actually the gradient here is given by that guy, and that would be the slope of our graph that was given to us. Okay, I think we've completed our analysis of what we have there. Let's just get to the question. It says now, which variable must be kept constant during the experiment? We can see that this is an experiment on Ohm's law. Of course, it took us a while to figure that out, so it has to be the temperature, because you just remember the definition of Ohm's law, temperature. Ohm's law says the potential difference between any 2 points on the circuit is directly proportional to the current passing through those 2 points when the temperature is maintained constant or is kept constant. So that is Ohm's law. Again, you wouldn't know if you looked at this directly. You'd be like, what the hell? What the hell? So you've got to play with what you know. Sometimes you don't win, sometimes you win. You decide again, because this can look a little bit too hectic, but this is something you do quickly, man. Because you look at what you have, you look at what you know, and you play with that. What is the polarity? Polarity of the connector point on the voltmeter connected to point X. Okay, great. So if you're looking at the circuit here, remember, current passes from left to right, isn't it? So we always move from positive to negative terminal. So it means this is connected to the positive end of our voltmeter, and that should be the negative end of our voltmeter, right? Right, so it means it's negative. Okay, easy mark also. Then the next question says, write down the mathematical relationship for the gradient. Okay, in this graph, the gradient we can see here, that looking at what we just interpreted, is actually r. Oops. It's r over the EMF, because that is what is the constant thing. Okay, so you get your 1 mark again. So 9.4 says, what does the y-intercept of the graph represent? Obviously the y-intercept it represents in our equation is the constant, so it's 1 over EMF. You walk away with your mark. So again, guys, please make sure you understand basic graphs and interpretations, but this question technically is not an easy question, because you need to understand what's going on. Otherwise you could easily get 0 here if you're not careful. So use the information on the graph to calculate there. So what are we supposed to use? The graph, not our own things, okay, to calculate the EMF of the cell. Not a problem. (9.5), we've got 9.5.1. So we know that the gradient M is equal to what? The gradient, we can see here that, hey, wait a minute. Is that the gradient? No, man, the gradient is given by let's think for a second. We want the EMF. And it's best if we use the y-intercept, because look, the y-intercept has a value right there. This is 1. Let's first count it. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is 1, 1, 2, 3. So basically this is 1, 3. So let's just use the y-intercept, because if we start doing the gradient, it's going to cause us to sweat. So we can say y-intercept is equal to 1, 3. This implies that 1 over EMF is equal to 1, 3, isn't it? Because that's the y-intercept, the constant. Then here this is over 1, and then you do your mathematical gymnastics there. We can say therefore E is going to be 1 divided by 1, 3. Let's get that value right there. 1 divided by 1, 3. I'm 1 divided by 1, 3. Where did I get what I'm doing now? Whew. Now this is 0, 7. Remember, to 2 decimal places is going to be 7 ohms. All right. So you've got it, guys. Very easy. It looked a bit technical, but sometimes what guides you is the marks, that you don't really have to do too much. So I believe here is the correct substitution and the final answer, those 2 marks. And then now we're doing the last question here, which is 9.5.2. The next one says the resistor R. Okay, so what can we use here on our equation? I think we can use the gradient. So we know that the gradient here, let's just write words, is going to be, pick any 2 points. I can pick this point and that point. Any 2 points will work. So we're picking those 2 points. It's going to be change in y. Y there is what? 3, 1, 2, 3. So this is 3, 3 minus there it's what? 1, 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's 1, 9. Divide by, change in x is going to be 1, 5 minus 0, 5. Okay, we're using those 2 points. You just pick any 2 points. Then let's see what is the value there. So I think I'm making a mistake here. We counted 3, 3 here, right? Yeah, 3, 3. So we've got here 3, 3 minus 1, 9. Then divide by 1, 5 minus 0, 5. So this gives us a 7 over 5. So you don't want to round off. So when it's a nice fraction, you leave it like that. So we can say this implies, it implies what? We know that the gradient is ER, so this is R over E is 7 over 5, because we were told to show the expression for the gradient. All right, now we know that this EMF has been calculated, which also implies that R over 0.77 is equal to 7 over 5. And then you do your mathematical gymnastics. We know that R is going to be basically 7 over 5 into 0.77, literally. But you can decide to multiply and divide. For me, I use shortcuts, man. I was taught maths properly. So if you were taught maths properly, you will know that certain things you don't need to repeat the standard ways for grade 8s to do that. But for you, you kill the bull, eh? So this is 1,008 ohms, okay? From what we did. So that is the story. right there. So it's a matter of just doing the math, okay? Easy, guys. So yeah, we're losing a bit of time, but let's try and see if we can get to 30 minutes, you know. So that was 3 marks. So I believe for this situation, and we can simply say for this substitution over here, and the answer should have been 4 technically, but it's fine. Not a big deal. Now let's do the last question quickly. Question 10. So we are told here 4 resistors, a switch, 2 voltmeters, and a battery are connected as shown in the circuit diagram below. The battery has an EMF of 10 volts. Okay. Switch S is open. When switch S is open, it means what? There will be no current passing through here. If the current is not passing through here, what do you expect? This voltmeter should not have a reading at all. So this voltmeter will say there's no current passing, then it should effectively read the EMF of the cell. Because this is basically, if you think about it, this V2 becomes the voltmeter across the terminals of that battery when there's no current passing, because here there's nothing. So it becomes the voltage across the terminals of the battery when there is no current. So it reads the EMF, okay? Great. And then, of course, if we close this, then it will read something. Of course, it will depend on that resistance. Obviously, we say this is negligible. So when this is negligible, we assume it's 0. So that will read 0 once the current passes. So these are some of the interesting things, you know, that you want to keep in mind. Okay, so easy stuff again. What is the direction of the flow of current? Is from the positive terminal all around the circuit to the negative. But we know here we've got a parallel connection. And then here they come together. And the circuit is completed, provided switch S is closed. Now, there comes a question. Write down the reading on V2. Remember, V2 is when the switch is open. So to answer 10.1, we know that it is going to read 10 volts. It reads the EMF because it is as good as the voltmeter across the terminals of that battery. Just don't worry about the distance away. It's fine. That's what it is, okay? Now, when switch S is closed, okay, now we have a full circuit. It's completed. Then we'll start to have a current passing. It says now the reading on voltmeter V1 is 2 volts, okay? Write down the reading on voltmeter V2 after the switch S is closed. Remember, we always assume that the resistance of the connecting wires is negligible. So basically, if you think about it, V2 is going to be equal to I times R. But now we're saying the resistance is 0. So this is I into 0, which becomes 0, okay? So you can think of a calculation to express that. So it becomes 0. Okay. 10.3 says calculate. So now there's a bit of action here coming. So we've got 10.3.1. The resistance of the parallel connection, easy. So R parallel is going to be product, which is 10 multiplied by 5, divided by sum, which is 10 plus 5. You can show the calculation. I mean, you can show things. I mean, this is 3 marks. So this is 3 marks. So perhaps you may want to say things like this. I don't know if they will punish you for this, but let's just try to be as standard as possible. We know 1 over R parallel is going to be 1 over R, 1 over 5 ohms. Plus 1 over 10. Therefore, R parallel is going to be the product, which is 5 times 10 divided by 5 plus 10. So we've got 50 divided by 15. So this is 3,33 ohms. Okay, so that, and that, just to try and show you where the marks are. But even if you did the product over sum, you would get a mark for that expression. You get another mark for those gymnastics. So you get 2 marks for that setup and then the answer. So I doubt if you would be taken down for not showing all of those things, okay? So it looks like we need a bit of space here. Okay, 10.3.2 is the resistance of R. Okay, not a problem. We can handle that. It's 5 marks. You can see there's a lot of work to be done. So what do we need? First of all, we need the total current. How will we find the total current? We know that what passes through resistor R is the total current, né? And we know that V1 is 2 volts. Okay, so will we know the total current? The answer is no. Okay, so we need to be smart about our business. We play it just right. So what do we know? We'll use the EMF calculation. But if we use the EMF calculation, nobody spoke about the internal resistance here. So we will assume it does not play. I think this is a dangerous statement even, because they should have mentioned for us that the internal resistance is negligible, but the diagram already doesn't capture it. If it is present, you will see a little drawing there, and this is captured under the EMF. So when it is not there, we assume it is not there. Okay, so we will assume that the external voltage is effectively the EMF. So let's see. I think we will need some sort of simultaneous equations here. If we look at the resistor R, what can we learn here? We will learn that V1 is equal to I tot times R. Now this is 2 over I tot times R. Therefore, if we want the total current, we will see that it is going to be 2 over R. We can make this equation 1. Alright? Do the things when I'm on. Okay, we make that equation 1. Now, we can say now, what else do we know? Well, we also know that for the EMF, in this case, okay, maybe let's just say also, we also know that the EMF is going to be the total resistance times R times I tot. That's what we know. EMF is given as 10 equals, the total resistance is going to be R parallel, which we got 3,33 plus the 2 of that 2 ohm resistor plus R, which we don't know, multiplied by R tot. Sorry, by I tot, which is now effectively 2 over R. Okay? Yeah, my lord. Yebo, 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 yes, which also implies that we've got, now we just do some gymnastics here. What we can do to save ourselves the trouble, we multiply by the common denominator R. Okay, we're going to be having 10R equals basically 3,33 plus 2 plus R into 2, which also implies that we've got 10R equals, let's sort this out, 3,33 times 2 is going to be 6,66. 6,66. In fact, let's just do this, 3,33 plus 2. Then we multiply that by 2. It gives us 10,66. plus 2r. Okay, great. Then we sort it out. I don't want to prolong this, I'm tired. So you know guys, what are the gymnastics necessary here? You just take 10, you subtract 2, you get 8. So basically you're going to have 10,66 divided by 8. Okay? So 10,66 divided by 8 is 1,33 ohms. Okay guys, that's it. So you can see here 2 steps were necessary. I kind of complexed the other step already, but you need to be, a bit crafty when you do these things. But yeah, we'll deal with that a little later. So 5 marks is good. So Ohm's law and that equation is important. And then here it's basically the substitution into this one and the answer. Again, they're giving 5 marks, so we only have 4. I suppose we're using, I don't know, maybe we can get a mark here. Where do we get an extra mark? Let's just say 2 marks for the answer. It's fine. Sometimes it's not easy to see where these marks come from. So we're told here that the 5 ohm resistor is removed from the circuit. Okay, so what happens when we remove this one? It means that the current no longer goes in here. So it basically goes that way. So we are removing the parallel connection. We're leaving the connection in series now. So all that is going to happen here, we know that the R tot is going to increase because once we remove that parallel connection, the total resistance will increase. And it means the I tot is going to decrease. Okay, so that is the 2 main things that are going to happen when we remove that 5 ohm resistor. Okay, it says now, how will the following values change? Choose from increases, decreases, or remains the same. Thankfully, they didn't say explain your answer, which is also a nightmare sometimes. So 10.4, we've got 10.4.1. What about the total resistance of the circuit? We can see that it increases. 10.4.2. The reading on voltmeter V1. What happens to voltmeter V1? Remember, this one is a bit technical. We know that V1 is equal to IR, right? This R in V1 is constant, but what happens to the current? It drops. So that means this whole product will drop. So V1 decreases. Okay? So that is it, guys. This is how you can go through a paper like this. I felt this paper is a little bit difficult as we're going through it. So I can see that these guys were truly tested. Okay. Again, it doesn't mean though that the questions are outrageous. They are quite good. And in fact, it's an excellent paper. You didn't hear me complain about this and that and that and that. So this paper was well moderated and well, planned and executed. So in 2021, these guys were on point. You wouldn't think that there was this stupid thing called Corona at the time because, things were just not reassuring. So, yep. So this is it, guys. So I would advise you that you take this paper, you work through it after this review, okay? And then make sure you read around the topics that I emphasized here and play a lot with the formulae that you are provided, because you can see that sometimes they present you with a nightmare like this one. I feel this question was the higher order type of a question, and of course they knew you could lose marks, so they kept them low. All right, and I think this is it, guys, and goodbye. just do yourself a favor, revisit this paper, read everything you have come across, especially in this channel. And of course, don't limit yourself to my channel. There's plenty other good guys that are also providing the best of, techniques and information, and demonstrating their abilities as well. So yeah, expand your knowledge as best as you can for maximum benefit. Otherwise, goodbye from me. I'll see you next time.